A Rankine cycle is constructed with no regeneration or reheat. However, it has a throttling valve between the steam generator and the turbine. The condenser pressure is 10 kilopascals and the steam generator pressure is 10 megapascals. The pump is reversible, but the turbine efficiency is only 85%. Assume that the exit of the condenser is a saturated liquid. With the throttling valve fully open, the turbine exit quality is 95%. If the throttling valve were adjusted to give a saturated vapor at the turbine exit, by how much would the turbine work in kilojoules per kilogram reduce? Draw the cycle on a TS diagram showing the effect of the throttling valve adjustment. So this is a Rankine cycle question, so as usual we need to understand what all of the components are in this Rankine cycle. Now notice there's no mention of any reheat or regeneration. In fact, it states explicitly that those are not occurring here. So this is a basic Rankine cycle, except that it has one extra component. There's a throttling valve between the steam generator and the turbine. So when we draw our sketch of the system, we certainly need to include that. So these are the four basic Rankine cycle components: pump, steam generator, turbine and condenser, but also a throttling valve. So properties we were given in the problem statement: the condenser pressure is 10 kilopascals, the steam generator pressure is 10 megapascals, we're told that the turbine efficiency is 85%, and we're told two different conditions for the exit of the turbine depending on the throttling valve setting. So when this throttling valve is completely open, the quality at this point is 95%. But when we partially close this throttling valve, this point becomes a saturated vapor. So after the valve is adjusted, 0.5 is a saturated vapor. And that's all of the information that we were given in the problem statement. So what we've been asked to find is the reduction in turbine work when the throttling valve is adjusted, and we're asked to draw a TS diagram showing the effect of the throttling valve adjustment. The assumptions we'll be making along the way: this is a steady state analysis, so nothing changing with time. The turbine and the throttling valve we'll be assuming to be adiabatic, so no heat transfer, and we'll be ignoring kinetic and potential energy changes everywhere in this system. So because we're interested in the work produced by the turbine, we're going to be looking at the control volume energy equation. So this is the complete equation shown here. Because we're assuming steady state, the left-hand side will be 0. When we apply this to the turbine or the throttling valve, it's adiabatic, so Q is 0 as well. Work we'll need to retain for the turbine, but not for the throttling valve. And kinetic and potential energy changes are going to be ignored everywhere. So when we apply this equation to the turbine with those assumptions, we get that the work of the turbine is equal to H4 minus H5. And notice this work is written on a per unit mass basis. So we've divided the general equation by the mass flow rate. So W turbine is H4 minus H5. And if we go back to our schematic diagram, we see that's the decrease in enthalpy across the turbine. Now, the enthalpy change across the throttling valve is 0 regardless of the valve's position. So when the valve is completely open, H3 equals H4, and when the valve is partially closed, H3 equals H4. So that means that between the two conditions described in this problem, before and after the valve is adjusted, H4 does not change. So the H4 in this equation is going to stay constant. There's no change in H4. The change we're going to see is in H5. So it's a change of the exit conditions that changes the turbine work, not a change in the inlet conditions. So H5 at the exit, before the valve is adjusted, the pressure there is 10 kilopascals and the quality is 95%. So we can go to table A3 and be able to calculate that H5 is 2,464.99 kilojoules per kilogram. After the valve is adjusted, the pressure in the condenser is still 10 kilopascals, but now that point is a saturated vapor. So table A3 would tell us that the enthalpy is now 2,584.7. So notice the enthalpy at the exit of the turbine has increased. So this is increasing, so it means the work is going to reduce because H4 is staying the same. So now we can go ahead and calculate the change in the turbine work. So I'm going to call that change in the turbine work delta WT. So we'll calculate that as the turbine work before the valve adjustment minus the turbine work after the valve adjustment. So that's the enthalpy change before minus the enthalpy change after. So notice this is why H4 doesn't have an effect on this problem, because it doesn't change. It cancels out of here because we're looking for the difference or the change in the turbine work. So this just becomes the difference between the enthalpy at the exit before we make the adjustment minus after. So putting those two numbers in there that we looked up in table A3, we get that the change in turbine work is minus 119.71 kilojoules per kilogram. So we can make our conclusion that when the throttling valve is adjusted, the turbine work reduces by 120 kilojoules per kilogram. Now we were also asked to draw a TS diagram of this and show the changes on that diagram that result from the throttling valve adjustment. So we'll do that next. So TS diagram, so vertical axis will be temperature, horizontal axis is entropy. So because we're working with water here, we always want to show the saturated liquid and saturated vapor lines. So liquid region here, mixture, and superheated vapor. The condenser pressure will be a relatively low pressure down here at 10 kPa, so that's a horizontal line inside the liquid vapor region, and it angles up like this. So that's our 10 kPa, the condenser pressure. And the steam generator pressure is a relatively high pressure, so I'll show that up here, and that's 10 megapascals. And in the liquid region, these lines, they actually go down almost perfectly on top of the saturated liquid line, but typically we show a little bit of separation there just so we can see what's going on in that liquid region a little bit easier. Now in terms of showing the cycle on the TS diagram, we'll start off at the inlet to the pump. So the exit of the condenser, inlet of the pump, is right here at state point 1. If you look for that, you can look for that numbering back on our schematic diagram. And that's the inlet to the pump, saturated liquid at 10 kPa. It's an isentropic pump, so on the TS diagram it goes straight up. So point 2 is right there, the inlet to the steam generator. Steam generator is constant pressure heat addition, so we go up there to saturated liquid, across to saturated vapor, and then up into the superheated region. So point 3 is going to be along here somewhere. I'm not going to put point 3 just yet. I want to talk about the exit of the turbine first. So the inlet of the turbine is somewhere along here, and then we drop down to the condenser pressure through the turbine. And because we were told that the efficiency of the turbine is less than 100%, as we drop down, we'll drift over to the right, so there'll be an entropy increase. Now before the throttling valve adjustment, the exit of the turbine has a quality of 95%. So it's inside the liquid vapor region, perhaps somewhere there. So I'll label that as 0.5. And so the turbine process needs to get to 0.5 from the 10 MPa line drifting to the right. So I'm going to say that our inlet condition is there somewhere. So that point there is 0.3, but it's also 0.4. So before the throttling valve adjustment, 0.3 and 0.4 are in the same place because the throttling valve is completely open. So the properties in front of it and after it are the same. Now we adjust the throttling valve by closing it a little bit. And the effect on 0.5 is to move it over here to the saturated vapor line. So our new 0.5 is right there. Now the turbine is still 85% efficient, so it's still going to move to the right as it moves down. But what's going to happen is 0.4 is now going to be down here somewhere. So this process from 3 to 4 is the throttling process. So that's a line of constant enthalpy, because even though 0.4 has moved down there to a lower pressure, So there's going to be some pressure now downstream of the throttling valve, which will be the new inlet pressure to the turbine. So our new point 4 is right here, and our new turbine process looks like this. So the enthalpy at 3 and at 4 is still the same. So the inlet enthalpy of the turbine hasn't changed, but the enthalpy at the exit has increased because we've gone from a mixture to a saturated vapor. So the work output of this turbine has decreased. So going from here to here produces more work than going from here to here. So that's a TS diagram for this Rankine cycle, showing the turbine process before the valve adjustment and after the valve adjustment.